Today we're going to look at rational inequalities. So continuing to work with these rational functions, trying to sketch them out, but also asking questions like when are they greater than a certain value? Not necessarily just zero. We could also ask questions about when we're greater than or less than a different constant, or even greater than or less than another function. So for this first section, we have the graphs drawn for us to get us started, but then the next section is going to be a little bit harder. We'll have to sketch out the graph. Okay, when we work with rational functions, we want to think about our domain. When we're dividing by x, we can cause some issues when we divide by 0. So we will first want to consider our denominator and figure out when would that denominator give us 0. Well, for this, there's two places this would be equal to 0. We can solve this. We get plus or minus 2. So plus or minus 2 are our domain restrictions. We cannot include those values because that would be dividing by 0, which is undefined. And we can verify that on the graph they've already got for us here. There's two breaks in our function at -2 and +2, our two vertical asymptotes, two places where our function is undefined. Now we can use this graph to answer a question like this. When is the function greater than 0? So all that's asking is when are our outputs greater than 0? When are we above the x-axis? Okay, so this whole section is above the x-axis. And then this section is also above the x-axis, seemingly forever. Right, it looks like we have a horizontal asymptote at 0, since we're bottom heavy. And we're never going to drop below that as we head off to infinity. Okay, so what are these values? We are going to give intervals here, just like we did with our domain. So it looks like starting at this asymptote at -2, up until we cross the x-axis, up until 0, we are greater than 0. Okay, and again, this is from this x to that x. This is an interval. Okay, we have another section over here starting after this asymptote, so starting at 2 and going on to positive infinity. So we're above 0 at that point. When are we greater than or equal to 0? Well, we can make a small adjustment, just change this to a bracket where we actually touch 0. We could also ask when we're less than or equal to 4, so we could use this line drawn across here at 4 to help us see what value is sort of our intersection point. At -1.66, you see that we switch from being above to below that 4. So we could use that to build our interval. I'll leave that one for you. But let's take a look at this one. So we're now comparing this function, the same function we had before, to this linear function. When is it greater than this line, x plus 1? So we're going to do a similar process. We're just going to think about when is our output of our rational section greater than the output of this line. So anytime on the graph we are above that line. So it looks like we're above the line there, and then we drop below. We're above the line here, and then we drop, and this section over here. So let's see if we can figure out what those intervals are. So first one, we start at -infinity up until that point right there. This is the x value where this switches. So I'll say -2.925. Notice it's just greater than, not greater than or equal to. So I don't need brackets. Okay, and then we are above, starting after our asymptote, up until -0.552. And finally, I didn't plan this well. We're going from 2 up until this point, 2.477. So just using those points that are given to me to define the boundaries of those intervals where we're above that line. Okay, so now let's try on the back side. There's a few problems that are a little bit tougher. This time we don't have a graphing calculator. They want us to try this without. So let's see if we can get there. Okay, so now we have 1 over x plus 4 is less than 0. The first step is going to be to try to sketch out this function. So first thing I notice is we're going to have a vertical asymptote at x equals -4. Remember, we have vertical asymptotes when we divide by 0. And I can see that if x is -4, we're going to be dividing by 0. We can also think about our horizontal asymptote here as well. This function is bottom heavy. We have a higher degree on the bottom, so it's got a big O, y equals 0. Okay, so we're going to have an asymptote at 0. So that tells us where the function goes on the ends. And then we have an asymptote, a vertical asymptote, at x equals -4. Okay, we might also think about our x-intercepts. X-intercepts are the zeros of the top, the numerator. But since we just have a constant on top, I know that numerator is never going to be 0. So we are not going to touch the x-axis. That makes sense since our horizontal asymptote is 0. We can also do a quick little y-intercept. So if I plug in 0 here, that would give me the y-intercept. When x is 0, we're on the y-axis. So we touch the y-axis at 1/4. So that might be a useful point to have. And indeed it is. It's going to tell me a lot about this function. Okay, I know I have to start here at this y-intercept. That's what I got when I plugged in 0. And then I could go up or down, but I know I don't touch the x-axis. We have no x-intercepts. So we must be heading up here at the asymptote. Again, we don't touch the x-axis, so we're just going to approach that horizontal asymptote at 0. So we've got a function that looks kind of like this on this side. Now, thinking about our behavior at the asymptote, since we go to positive infinity on the right side, we must go to negative infinity on the left side as we approach that asymptote. Remember, we know that because of our multiplicity rules. There's only a single factor on the bottom for that asymptote, so we know the function is going to split, going opposite directions. Okay, so now that I've got it sketched out, I can answer this question. When are we less than 0? So here's the outputs of the function we've sketched out here. It looks like this whole section over here is below the x-axis, less than 0. So negative infinity up until our asymptote at -4. All right, let's try a few more. I'm going to go ahead and skip this one. You can use number 2 as a practice. Let's take a look at number 3, which is a little more complicated. Okay, so first thing I notice is the top of this function is not factored. I'm going to go ahead and do that. That'll make it easier to see the zeros of the top. So it looks like if I do x minus 1, x minus 6, we will multiply to get positive 6 and add up to -7. You can use your box model or your X puzzle to help you solve this little puzzle. Okay, so now I have that, and it'll make it a little bit easier to sketch this out. So first thing I have is my vertical asymptote at 5, right? Because that's the 0 on the bottom. We can get our horizontal asymptote, or can we? This time we have a higher degree on the top, so we don't have a horizontal asymptote. However, we do have a slant asymptote. Our degree is 1 higher on the top than it is on the bottom. So we'll cover that in a second. But first, let me get those x-intercepts. So we already have the top factored. That is showing me that we have 2 zeros on the top, 1 and 6. That's going to be useful to help us kind of piece this together. All right, so x-intercepts at 1 and 6. Okay, let's talk about that slant asymptote. So we have an oblique or slant asymptote anytime that our numerator is 1 degree higher than our denominator. So we can figure out that oblique asymptote by doing a quick little division. So I'm going to do synthetic division. I'm just going to take the coefficients of my top, 1, -7, 6, and I'm going to divide by our factor, which is x equals 5. Notice we do the value of x, positive 5, not the factor, -5, or the x minus 5 there. So synthetic division, we're going to bring down this 1, then we're going to multiply, add, multiply, multiply, add. Okay, so we've done our synthetic division here. This right here is our asymptote. So x minus 2, this is the asymptote, y equals x minus 2. We don't care about the remainder. You can just ignore that. It is kind of useful if it turns out to be 0, it shows you a factor. But I'm just kind of curious about what this function looks like, so I can sketch it out. I kind of encroached on my graphing space here, but that's okay. So this line, y equals x minus 2, we got from dividing here, is our oblique asymptote, our slant asymptote. Okay, so now let's see if we can piece together what this function looks like. So we know we have an x-intercept here at 6, and then let's go this way. Let's get our y-intercept real quick. We didn't do that one yet. So what would happen if I plugged in 0? If I plugged in 0, we would be left with -6/5. So y-intercept of here. And that's a nice useful point. Starting to kind of piece together the shape of the graph. So it looks like we're going to go something like this. We're going to approach that asymptote as we go left, that slant asymptote. And then we have this vertical asymptote that we cannot cross. So I think our function is going to look something like that. We have single multiplicity on the bottom, so I know that the function is going to split at the asymptote. So down here, and then we're going to approach our slant asymptote on the ends. Okay, so pretty tricky there. That's a tough one to draw, but we can get it done. You can check Desmos to make sure that looks right. Now we can finally answer the question, when is the function greater than 0? Well, we start being greater than 0 right here, and then through that section. And then this section over here, we're also greater than 0 or above the x-axis. Notice this time we're greater than or equal to 0, so we'll be careful about our brackets. Okay, so this x-intercept we said was at 1. So from 1 up until our asymptote at 5. And then from 6, notice there's this little section down here from 5 to 6, this little section that is not above 0. So 6, and I'm going to need brackets for that. Sorry, y'all, it's a mess. From 6 to infinity. Okay, so just some more problems to consider. Once you're finished with this, there's those practice on AP Classroom to work on. I'm going to leave this last one for you to consider. That one's pretty challenging. See what you can do about graphing y over x. That's just our parent function, rational function. And then graphing the line y equals x. So y-intercept of 0, slope of 1. So a little bit trickier. Again, don't feel bad about jumping on Desmos to check your answers if you get stuck.